Hello everyone, welcome to this session. In this session, I will explain first order ordinary differential equation solving method called Euler method. In this session, I will explain its theory and its Python code. So let's start. In mathematics and computational science, the Euler method, also called the forward Euler method, is a first order numerical procedure for solving ordinary differential equations, says ODEs, with a given initial value. It is the most basic explicit method for numerical integration of ordinary differential equations and is the simplest Runge-Kutta method. The Euler method is a first order method, which means that the local error, that means error per step, is proportional to the square of the step size, and the global error, that means error at a given time, is proportional to the step size. The Euler method often serves as a basic to construct more complex methods, for example, predictor corrector method. In this session, I will explain its geometrical description also. So, let's consider the problem of calculating the shape of an unknown curve which starts at a given point and satisfies a given differential equation. Here, a differential equation can be thought of as a formula by which the slope of the tangent line to the curve can be computed at any point on the curve. Once the position of the point has been calculated, the idea is that while the curve is initially unknown, its starting point, which we denote as say A naught, is known in the question. It is given in the question. Then from the differential equation, the slope to the curve at A naught can be computed, and so the tangent line is to be computed. Then a small step along the tangent line up to a point, say A1. Along this small step, the slope does not match too much, so A1 will be close to the curve. If we if we prevent that A1 is still on the curve, the same reasoning as for point A naught above can be used. After several steps, a polygonal curve is computed. In general, this curve does not diverge too far for the original unknown curve, and the error between two curves can be made small if the step size is small enough and the interval of computation is finite. Okay, here I have plotted this unknown curve. Uh, this is the known curve. This is the unknown curve. That means the exact solution of the problem. And the initial point is given as t naught and y naught. In this point t naught, y naught, we have draw a tangent, and this tangent we and from this tangent we will get the next point, say t1 y1. From the next curve you can show this is the f of t versus t graph, and this is the exact solution of the differential equation. And at first in the question the a naught point is given, and from the point a naught we have draw a tangent, and from then we get the next point, say a1, and 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 that point a1 we have also draw a tangent, and from this tangent we will get the next point, say a2, and from this point a2 we once draw the next tangent, and from this tangent we get the point a3. In this way we have got a polygonal shaped curve. This is drawn in the figure, and this is nearly close to the of these exact solutions of this differential equation. Okay, I think this is clear to you. Next, I have written the first order processes. When given the values for t naught and y of t naught, and the derivative of y is a given function of t and y denoted as y prime t is equal to function of t comma y of t. Begin the processes by setting y naught is equal to y of t naught. Next, choose a value h for the step of every step along t-axis and set tn that is equal to t naught plus n into h, or equivalently we say that tn plus 1 that is equal to tn plus h. Now the Euler method is used to find yn plus 1 that is equal to yn plus h into f of tn comma yn, where n is the number of steps and h is the step size. The value of yn is an approximation of the solution at time tn. The Euler method is explicit, means it uses the previous value of y of x and the slope of the tangent line at the point to estimate the next value. We know that the derivative of a function is equal to the slope of the function itself. Okay. Next, I have written its limitation. The Euler method is relatively inaccurate. That means, especially for large step sizes or when the solution curve has significant curvature. From, sub, from For some precise solution, more advanced numerical methods like Runge-Kutta methods are often used. Next, I have written four numerical problems based on Euler method. The first question says that a first order differential equation is given as below, that is dy dx is equal to e to the power y into sin x, with the initial value is given that x equal to 0. At a point x equal to 0, the value of y is 0, and then create a list, say x, with 100 x values between the range 0, 1 and write a Python program to solve this differential equation using Euler method for x values in the list x. It is given that the exact solution is yx that is equal to minus ln cos x, and finally compare the calculate and exact values at x equal to 1 and print both the values. These four questions are almost same. Next I will show you its Python code. Here I have written its Python code. As usual, at first I have import some packages as import numpy as np for defining the function and for defining the x domain. Then import matplotlib.pyplot as plt for plotting this function. Here I have written some initial conditions, that is x naught is equal to float. Here I have inputted these values float input and enter the initial point, and y naught float input enter the value of y at initial point, and next I have input n that is equal to int input enter the number of steps, and h is equal to float input enter the step size. Then I define the differential equation, say dy dx that is equal to f of x comma y, and I have defined the function as def, which is the keyword, and f x comma y, and return the function. The derivative of the function is x exponential of minus y. And then I have written the Euler method, say def, using the function def Euler. I have taken the name of the function as Euler, and if x naught, y naught, h, n are the arguments. And next I have written x values is equal to a list in the list in which the elements are x naught, and y values are a list also, and the elements of this list is y naught, and I have taken x is equal to x naught and y is equal to y naught, and then I have written a loop for in range n y is equal to y plus h star f of xy. This is the Euler method formula, and x is equal to x plus h, and this is the steps. Then I append the values x values dot append x and y values dot append y, and then return x values comma y values. And then I have written the exact solution which is given in the question. So DEF exact solution, and this is the function name and x is a variable, and then return np dot log x squared divided by 2 plus 1, and then print exact value of the solution, that means exact value at a point 1. Okay, in this question given that print the exact solution at a point x is equal to 1, and this is the command that print exact value of the solution, that exact solution bracket 1, and then print calculated value of the solution by Euler method, and then print the error, that means the exact solution minus the Euler method solution. Okay, and then get Euler approximation, that is x Euler comma y Euler, that is Euler if x naught y naught h comma n. Okay, and then get exact solution x exact. I have written the domain x dot linspace x naught comma x naught plus in cross h and comma 100. I have taken the number of points as 100, and the initial point is x naught and the final point is x naught plus n star h, and y exact is equal to exact solution bracket x exact. Okay, then I have plotted the exact the unknown curve and the exact solutions. PLT dot plot x Euler y Euler and level Euler method, and also PLT dot plot the exact solutions. Okay, and here I have give the title that Euler method versus exact solution, and PLT dot show for showing the function. Next, I have run this code. Please wait a minute. Here, enter the initial point that is given in the question is 0, and then enter the value of y at initial point, that is also 0, and then enter the number of steps I taken is 100, which is given in the question, that is 100, and enter the step size, that is 0.01, and then we get the result, that is the exact value of the solution is 0.405, and the calculated value by Euler method is approximately 0.402, and the error is 0.002, which is very less. Okay, and you see the graph, that Euler method versus exact solution graph is that here you see that the Euler method graphs is so blue color, and the exact solution is the curve which is shows the red color, and you see that the two curves are overlaps. Okay, I think this is clear to you, and I hope that you will solve the four problems yourself. Okay, and thanks for watching this video.